Hello. In this video I provide demonstrations of how to carry out Poisson and negative binomial regression in SPSS using an offset variable. The demonstration uses SPSS version 25. A link for the data that I use as well as this PowerPoint will be made available for download underneath the video description. Additionally, a running document containing links to other videos on Poisson and negative binomial regression and using other programs will be made available as well. So, as a general overview, Poisson regression and negative binomial regression are techniques that are used to predict count outcomes, with those counts occurring within a given space or span of time. Oftentimes the observed counts reflect low-frequency events. Unlike OLS regression, Poisson and negative binomial regression do not assume normally distributed residuals with constant variance. They also do not assume a linear relationship between the independent and dependent variables, as is required using OLS regression. Poisson regression makes the assumption that the conditional mean and variance of the distribution of counts are equal, a condition referred to as equidispersion. In many cases, the variance of the count outcome is greater than the mean, referred to as overdispersion. So when overdispersion is present, the Poisson model can underestimate standard errors that lead to an increased likelihood of committing a type 1 error when making inferences about regression parameters. When overdispersion is a problem, one possible solution is to use negative binomial logistic regression. Another possibility is to try a different scaling parameter, but our main focus in this video is going to be on using negative binomial regression. Frequently, Poisson and negative binomial regression are used when counts have been made within a fixed interval of time, that is, the measurement period is the same length for all cases. However, in situations where counts are made over varying periods of time across cases, then it becomes necessary to control for differences in the length of the periods in which observations are made. This can be accomplished through incorporation of an offset variable. In effect, an offset variable is used to account for different levels of exposure associated with the cases under observation. In SPSS, the offset variable is created by computing the natural log of a variable reflecting the length of the observation period associated with a given count. This variable is then incorporated into the model as a predictor with the regression coefficient fixed at 1. Now let's briefly talk about model fit. So in general, the first step in assessing model fit with Poisson and negative binomial regression is to evaluate the results of the likelihood ratio chi-square test. The likelihood ratio test is used to test whether the model containing the full set of predictors represents a significant improvement in fit over a null or intercept-only model. When the likelihood ratio test is statistically significant, this means that the model represents a significant improvement in fit relative to the null model. Only when this model is significant do you proceed to evaluation of each of the regression coefficients to determine those predictors that contribute significantly to the model. There are two basic tests of the regression coefficients in Poisson and negative binomial regression. One is the wall test, the other is a likelihood ratio test. A limitation of the wall test is that it can be overly conservative when it comes to testing the regression coefficient against the null. The likelihood ratio test is a more powerful test of the regression parameters. It involves testing the full model that includes a given predictor against a reduced model that excludes that predictor. If the decrease in fit is statistically significant, then this indicates that the predictor is a significant contributor to the model. Now in general, the Poisson regression model is simpler than the negative binomial model. Unlike the Poisson model, the negative binomial model incorporates an ancillary parameter that is designed to account for the degree of overdispersion in the conditional distribution of the count outcome. The Poisson and negative binomial models can be compared to gain insight into which represents a better fit to the data. The judgment of a relative fit can be based on comparisons of the log likelihood, Akaike's information criterion or AIC, and Bayesian information criterion or BIC. The AIC and BIC account for model complexity when evaluating relative fit. Assuming equal levels of absolute fit between competing models, the AIC and BIC should select the model that is more parsimonious. When evaluating the log likelihood, AIC and BIC, the preferred model from a set of candidate models will be the one with the lowest values on these indices. In those cases where these indices are negative, the preferred model is the one with the most negative values. So the absolute size of the value for these indices isn't what matters, rather it's how negative the indices are. So here's just a little snippet of our data. So we're analyzing data based on adults' responses to questions from the General Social Survey. In this example, we will be modeling the number of children a person reports having had as a function of the gender identification and education level of the person. Gender identification in this data set is called female ID, that's the variable name, and it's coded 0 for male identification and 1 for female identification. And education level is coded into 5 levels, where 0 is very low and 4 is very high. The natural log of the person's self-reported age will be included as an offset or exposure variable, which is to account for different exposure levels for the individuals. In a nutshell, the exposure variable captures between person differences in the degree of opportunity for the event counts to accrue. Sorry about that. And this actually makes sense to use age as that exposure variable, because individuals who are older would presumably have more opportunity to have more children than younger individuals. So we're going to begin by analyzing the data with Poisson regression, and if there is evidence of overdispersion, which there will be, then we will then consider the negative binomial regression. So here we have our data opened up in SPSS, and there are several variables that are unrelated to our current analysis. The main variables we're going to be using are age, which we are going to create an offset variable for that, education, and female ID right here, and then the number of children is our dependent variable. So first let's create our offset variable by going to Transform, Compute Variable, and we're under target variable in this little box to the left. I'm going to type in ln.age. So this is an arbitrary naming. It doesn't, there's no formal naming system that's required. I'm just typing that in, and then under numeric expression you do have to have a certain structure. So I'm going to type in ln and parenthesis, and then we're going to move the age variable over to that box right here and end parenthesis. So when we click on OK, now when we look at our data set, we now have our new offset variable, which is the natural log of age. So next we're going to run our Poisson regression, and we'll do that by going to Analyze, Generalized Linear Models, click on it. Where it says Counts, we're going to click on Poisson log linear. So the next step, click on Response, move our dependent variable to the dependent box. Where it has predictors, we are going to move, in this case, we're going to move education to the factor box, and I'm going to move the female ID variable over to the covariates box. The reason why the female ID variable, true, it is a nominal variable, but it's already dummy coded, 0 for male and 1 for female identification, and it's perfectly permissible to include it under covariates. Education, I'm just going to go ahead and treat this as a factor variable, and we're going to click under Options right here, and I want the very low education group to be treated as my reference category. So to do this, what we're going to do is we're going to click under Descending right here, so that category is our reference category. So we'll click on Continue, and then we're going to move our offset variable down to the offset variable box. We'll click on the Model tab and move our variables over, our predictors over, and then under Estimation we'll leave everything pretty much the same. Under Statistics, I'm going to go ahead and click on Include Exponential Parameter Estimates, and then I also want, in addition to having walled chi-square tests, I also want likelihood ratio tests. So I'm going to click that little button right here, so that I can get that result as well, or that information as well. So next we'll click on OK, and we have our output. And so looking at this, you can see probability distribution is Poisson. We can kind of scroll down, you get some basic descriptive information. We have our goodness of fit table right here with various goodness of fit measures, and we'll talk about that shortly. Our Omnibus test, this is our likelihood ratio chi-square test I was telling you about earlier. Parameter estimates table contains our regression coefficients, standard errors, walled chi-square, and so forth. And then the test of model effects contains our likelihood ratio chi-square tests. Okay, so in terms of interpretation, let's just start off by noting that departure from equidispersion can be assessed using the ratio of the deviance or Pearson chi-square to the degrees of freedom. So we're basically looking at these values right here in our table. And values that are closer to 1 indicate equidispersion, values that are greater than 1 indicate overdispersion, and values that are less than 1 indicate underdispersion. So given that these values right here are both over 1, we are going to assume that our data are overdispersed, and then we are going to consider using the negative binomial regression model. Even so, what we're going to do is go ahead and quickly go through the remaining output in order to just finish up our interpretation. So our omnibus test contains our likelihood ratio chi-square test. So this is the chi-square value, degrees of freedom, p-value. And given that our p-value is indicating statistical significance, we would infer that our model containing the full set of predictors represents a significant improvement in fit over the null model, or basically an intercept-only model. Now down below you can see we have our parameter estimates table with our regression coefficients, standard errors. We've got the wall chi-square value right there, p-value, and so forth. And then up here in the table of model effects, we have our likelihood ratio chi-squares for the individual predictors. You'll notice that so we have female right here and female right here. You'll notice that with the likelihood ratio test, we have the entire education variable. It's basically an omnibus test of the education effect. So there's a likelihood ratio test and test value and p-value, and then down below under parameter estimates you'll notice that we've got these different predictors that are included, and these are dummy variables, and the reference category is actually reflected in the education group that is coded 0. So basically what each of the regression slopes that you see right here, these are comparisons between like for instance group 1 versus group 0, group 2 versus 0, 3 versus 0, and then 4 versus 0. So that's basically how it's laid out. So the likelihood ratio test basically tests the omnibus effect of that factor, and then the under parameter estimates, because we have dummy coded variables, each individual dummy variable is being tested for statistical significance. So let's look at our regression coefficients a little bit more closely. So we see that the regression coefficient for the female ID variable right here, it's positive, and that indicates that persons identified as female reported having more children than males, but we do see that it is non-significant, and it was actually non-significant using the likelihood ratio test as well. The education variables, as I said, are dummy variables, and the coding has the lowest education level group serving as a reference category. So we see that the regression coefficients for all the dummy variables are negative, suggesting that with increasing education the number of children a person reported was decreasing. All of those dummy variables were statistically significant in terms of their predictive capabilities. Okay, so next, given that we found evidence of overdispersion, now we want to run our negative binomial regression. So to do that, under counts, you're going to, instead of clicking Poisson log linear, we're going to click on the negative binomial with log link. So let me go back and I'll show you how to do that using SPSS. So here we are again, and we'll open up Analyze, go to Generalized Linear Models again. We'll click under Type of Model, we're going to click on Negative Binomial with Log Link. And the next thing that we're going to do is we're going to leave everything else exactly as it was before. Under Statistics, so we'll go ahead and click on Lagrange Multiplier Test, and I'll talk a little bit about that shortly. We'll click on OK. And so now when we're looking at our output, you can see it says probability distribution, negative binomial. You'll notice that we have the Lagrange multiplier test right here. And basically this is testing the null hypothesis that the ancillary parameter is equal to 1. And so, as I mentioned before, when you're running negative binomial regression, you have an ancillary parameter that accounts for departures from equidispersion. And so in this case, the estimate is basically 1, and this test right here is indicating significant departure from that null hypothesis. So down below we have the goodness of fit measures that we were talking about before, our omnibus test as before, our regression coefficients, and then our likelihood ratio and wall tests are provided as well. So once again, the Akaike's information criterion and Bayesian information criterion provide parsimony adjusted measures of fit and can be used to compare both nested and non-nested models. If comparing two or more models, then the model with the lowest AIC or BIC is the preferred model. And if two models are being compared and the AIC and BIC is negative for those models, then the model with the most negative value is the preferred model. So we see, just kind of this little note that I made down here, for the previous Poisson model the AIC was 64.25. For the current model it's 68.33. The BIC for the previous model, Poisson model, was 64.59. The current one is 68.66. So it looks like, based on these information criteria, that the previous Poisson model was actually a better fit to the data than the current negative binomial model. Nevertheless, we'll go ahead and just kind of scroll through. We have again our likelihood ratio chi-square test that is statistically significant, once again indicating that the model containing the full set of predictors represents a significant improvement in fit over an intercept only model. And then you can see with our parameter estimates with their respective Walt chi-squared tests and also the likelihood ratio test, basically the results don't differ from what we saw before with our Poisson regression model. Now, after clicking that Lagrange multiplier test, you can see again, this is what I kind of referenced before. And so the test is basically testing the ancillary parameter to see if it's significantly different from 1. Okay, and so if you do have statistical significance, then that's evidence that our model is misspecified with respect to the ancillary parameter. And remember, this is basically using the default in SPSS. And so you have to keep in mind that defaults don't always translate into a good model specification. So in order to get around this particular problem, or you might just completely choose to bypass this altogether and just go straight down to estimating the ancillary parameter and just avoid this particular issue. If you click under Custom, set the distribution as negative binomial, the link function as log, and then click on Estimate Value. That is basically how you can come up with perhaps a more calibrated estimate of the ancillary parameter. So for our walkthrough, we'll go through Analyze, we'll go back to Generalized Linear Models, and under Type of Models, instead of the negative binomial, we'll just click on Custom. Distribution, we'll set it as negative binomial. Link function, we'll set it as log, and then we'll set the estimate value down here. So we'll estimate the value down here for the ancillary parameter. So next we'll click on OK. And so now, looking at our output, you can see that this is the estimate for our ancillary parameter. It's 0.114, whereas previously, when we ran it, the ancillary parameter was basically fixed at 1 right there. So again, we have our goodness of fit indices, and I'll talk a little bit more about that in just a second. Our omnibus test is still indicating us that our model containing the full set of predictors represents a significant improvement in fit over the null model. You can see again, I've kind of highlighted our estimated ancillary parameter. Nevertheless, the results were largely the same as what we had before when we ran the initial Poisson regression and then using the negative binomial regression with the ancillary parameter fixed at 1. So looking at our results from the three different models, I will just say model 1 is Poisson, negative 2 is negative binomial with the defaults, and model 3 was the negative binomial with the estimated ancillary parameter. So you can see right here that the AIC for the initial Poisson, BIC for the Poisson, then you've got the negative binomial, the first one that we ran, and you can see that those values were higher than the Poisson model. But now you see that the AIC and BIC for the final model that incorporated the estimated ancillary parameter, that actually exhibited the lowest AIC and BIC values. You also see that with respect to the log likelihood. So basically what this is indicating is that our third model represented a better fit to the data than either the Poisson model or the negative binomial model that was estimated using the SPSS defaults. So that concludes this particular demonstration. If you look on the last page of the PowerPoint, there are various references and resources that you can look up, and I appreciate you watching. If you find the video useful and the materials useful, please take time to like the video and share it with others, and also please consider subscribing to receive information on new videos that I upload. So again, thank you for watching.